My name is Milan Tomin. I'm from Math and Physics Department at Queen's University of Charlotte, and thank you for being here. So at the beginning of this year, I did a research along with two of my physics professors as my mentors and co-authors. And the research was focused on projectile motion and its application in sport, particularly in American football. The research was published in the International Physics Journal, and I'll be glad to talk about it today. Projectile motion is an introductory physics topic focused on an object that analyzes an object projected, or in this case thrown, at an angle, which then follows the parabolic path. Parabolic path of an object is due to a combination of its velocity components, vertical and horizontal. In this research, we try to find relationship between running receiver, who is trying to catch the ball, and a quarterback, who passes the ball to the receiver. And even though in our original research, we analyzed two cases, today I'm going to focus only on case one, where the running receiver runs at constant acceleration. Case two was where running receiver ran at variable acceleration, which is more realistic model, but slightly more complicated. And in both cases, we had some assumptions taken in account in order to simplify the model, and those are the following. Both quarterback and running receiver are initially at rest and at the same location. As soon as the quarterback passes the ball, running receiver starts running, or vice versa. The ball has no spin, air friction was neglected, and the ball was projected and received at the same height above the ground. So when talking about projectile motion, some equations have to be introduced, and those are equations that allow this research to happen. We will focus on those equations. First of those defines distance ran by the receiver. Since the receiver starts running from rest, the first part of the original equation is left out, and the receiver runs at horizontal it runs in horizontal direction or in x-axis. Second equation calculates projectile's range, or in other words, it calculates the distance that the ball travels, horizontal distance. And the third equation calculates projectile's time of flight, or in other words, how much time does the ball spend in the air. And combining those equations, we can solve for the angle theta. Basically, substituting left-hand side of equation 1 with equation 2, where both equations define the distance, and substituting time from the right-hand side of equation 1 with equation 3, where both equations are equations of time, and manipulating the equations, we can get angle theta. So what is it? What is the angle theta? It's, let's say, magic angle that always ensures synchronous pass. The ball, when launched at an angle theta, the ball will always be delivered to the receiver. It only depends on constant acceleration, receiver's constant acceleration, which can be seen from the equation, and that's A. So it does not depend on how fast is the ball thrown. And that's one really important part. And here's the example. On x-axis we have receiver's constant acceleration, and on y the launch of the angle of the projection. So the bigger rate of acceleration the receiver has, the smaller angle of the projection is. And one interesting finding is that when a receiver accelerates at 9.8 meters per second squared, which happen to be the same as Earth's gravitational acceleration, angle of projection becomes 45 degrees. And that's the angle that maximizes range of the football. But someone might think, how does it make sense that if quarterback passes the ball at slower or higher speed, does not affect the synchronous pass? And it's true that if the quarterback passes the ball faster, the football will travel longer, But let's not forget about the receiver. Receiver keeps running as well. So what the velocity or speed of the ball, projected ball, determines is how long is the ball, and therefore how long is the receiver going to, how much time are they going to spend running, or how much time is the ball going to be in the air. And in this example, we have ball initial speed on the x-axis, and on y-axis, again, angle of projection. And no matter what speed we pass the ball, quarterback passes the ball, the angle in this case remains the same, in any case. But in this case where running receiver accelerates at 1.1 meter per second squared, which gives him around 9 meter per second speed at around 40 yard mark, the angle becomes 83.6 degrees. And lastly, I would like to state again that for the synchronized pass, for the perfect pass, in the case when running receiver runs at constant acceleration, the angle of projection depends only on theta, which depends only on receiver's acceleration, and it does not depend on how fast is the ball thrown. Thank you.